So, good morning, everyone. Today I'm recording for you the first part of lectures 9, 10, 11 about strategic games equilibrium. So, this is the outline of the presentation. I will go through the Nash equilibrium concept with non-discrete strategy space. And for the rest of the lecture, we'll continue in a second video. We'll talk then about polymetrics game Nash equilibrium formulation, different games in strategic form, and some applications, and we'll summarize. So what is an equilibrium with continuous variables? So sometimes the conflict studied involves, in fact, strategic decision variables defined on non-discrete sets. Many problems, in fact, in economics, marketing, finance are like that. And depending on the form of the game studied, in fact, strategic or extensive, and the order of play, the equilibrium concept can have different names. So for strategic form games with non-discrete strategy space, we recall the Nash equilibrium definition. And we said earlier on that the Nash equilibrium is a vector of strategies such that for every player, there is no interest or no incentive to unilaterally change our mind and play something else than the Nash equilibrium we agreed on. So for the mathematical notation, this is slightly different from what we've seen before. Here, strategic form game is gamma, and we have n is the set of players. I is the set of strategies for every player I in n. And f and xi is the fitness function for every player. So we assume that there is an empty set representing the set of game players, capital N. L and xi or I and fi, whatever you want to call it, is a non-empty set representing the interval of strategies available to every player I. And this I, big I, in fact, gathers all the set of possible strategy profiles we could all play as game players. So in fact, this defines the set of solutions to our game. So fi is a function from capital I into the set of real numbers R, which means it returns what? It returns a payoff for our player. So we also recall that each player expresses his decision using a vector xi or a decision vector xi, which represents, in fact, an allowable setting of his decision variables. So the Nash equilibrium conditions now rewritten in non-discrete space. So the strategy profile x hat is a Nash equilibrium if and only if the fitness provided by x hat for every player I in n dominates or is larger, equal, or greater or equal than his fitness if he deviates from his play in x hat. So he decides not to play x hat I, so he would play, for instance, xi. Okay, so we also add the condition that x hat I here should be within the interval of allowable feasible solutions or the interval for my decision variable, every player I. So some more math. So one can say that the strategy profile vector x hat is a Nash equilibrium if and only if for every player, we can say that x hat, in fact, is a maximizer for the fitness function when on all the set of possible solutions for my player I. So in other words, x hat I is the best response for player I, given what all the other players decide. In the general case, we assume that fi is at least twice differentiable. And we add also the fact that since we are looking for maximizers, we should talk about nonlinear optimization. So a strategy profile x hat is a Nash equilibrium if and only if for each player I, the first and second order optimality conditions are satisfied. And you may have seen this earlier on in your optimization courses. Linear or nonlinear optimization. We have so many courses like that. Basically, you have the first order conditions. Let's say that the gradient of my fitness function multiplied by any direction in the given strategy space could only deteriorate my function. And the second one would guarantee that you have a maximum because every direction will give you, in fact, a decrease. So The first condition means that any direction would deteriorate the objective. And the second condition means that the function is concave down because we have a maximum point. Okay, so I prepared for you this small example. We've solved it in class. So this is the price and warranty period example. And this is the last item we will have before the midterm as material for the midterm. So we said earlier in class that a conflict involves the manufacturer and the retailer of a given widget. And the retailer buys the widget at a given price, which is W, and sells it at another price, which is P. So the retailer here, he controls only P, while the market's demand for the widget depends on the price P and the warranty period T offered by the manufacturer. And we'll assume here that the demand function is capital D, which is A minus beta P minus gamma T. So the manufacturer, in fact, has no control on the unit production cost C for the widget. However, he controls the price W he bills to the retailer and the warranty period he would guarantee for the consumers. So to summarize, the manufacturer controls two variables, W and T, while the retailer controls one variable, which is P. And we also assume that the manufacturer's total warranty cost is omega of T, which is minus eta T squared. So we are looking to find the Nash equilibrium for this game. So here, what I'm going to do, I'm going to share with you my whiteboard, because we've solved this game, in fact, in class. And I'll share with you my whiteboard here. Okay, so let me go to the previous whiteboard I recorded. Yeah, this one. So yeah, this is the board I prepared for you. I prepared also the solution I will upload later on the Blackboard. So from the retailer's point of view, this is his utility function. He needs to maximize his total profit, which is R of P for the retailer, which is the demand multiplied by P minus W. P minus W, which is the price minus he bills to the consumers minus the price at which he buys from the manufacturer. And from the manufacturer point of view, he needs to maximize M of WT. He has two control variables or two decision variables, which are W and T. And he needs to maximize also his own profit, which is D times W minus C minus eta T squared, which is the warranty cost. So from the left side, if we differentiate with respect to P, we have the derivative of the R's utility function or profit with respect to P. We'll get the differential of the demand with respect to P times P minus W plus D. That's a simple product rule, which needs to be equal to 0. This is to satisfy what? The first order conditions. Okay. If you plug in here the derivative of the demand with respect to P, which is minus beta, you get minus beta times P plus W plus D. And if you plug in the expression of D we've seen in the slide, you get finally this equation. I'm calling it equation 1, which is minus 2 beta T plus gamma T plus A plus beta W equals 0. Okay. And if I look to the other side, to the right side now, I have two first partial derivatives. Derivative of M with respect to W, which gives you basically D equals 0, because here, if you differentiate with respect to W, you just get to 1. And of course, D equals 0 basically is somehow debatable. It means that the demand is equal to 0. So let's assume this makes sense somehow, but we've said many times in class that the game should be designed in a way that makes sense, okay? So if you substitute with the expression of D here, you get A minus beta P plus gamma T equals 0. So that's what I call second equation, equation 2. And the derivative of M's profit with respect to T will give you differential of the demand with respect to T times W minus C minus 2 eta T equals 0. The differential of the demand with respect to T is gamma times W minus C minus 2 eta T equals 0. That's my third equation. Now, if you want to solve these three equations, 1, 2, 3, simultaneously, what do you want to do? One way to do it is to go backwards. So from 2, you extract the following, that P star, which is the Nash equilibrium solution, is equal to A plus gamma T star over beta. That's easy to get. And the intention here is to get P in terms of T, W in terms of T, plug all of them in equation 1, and finally find the expression of T at the Nash equilibrium. From equation 3, we get W star, which is 2 eta T star over gamma plus C. We plug these two, P star and W star, in 1, and we get finally the following answer, which is T star, which is A minus beta C divided by 2 beta eta over gamma minus gamma. And it's easy because you will get just a linear equation in terms of T when you substitute back in 1. As a small numerical application we've seen in class also, we said let's now assume that A is equal to 10, beta equals to 2, C equals to 3, eta equals 1, gamma equals 1. And we found that T star was equal to 4 over 3, W star was equal to 6 and 1 over 3. And I think we found that P was equal to, P star was equal to, I think, 5 and 2 over 3. Okay. And you will have to criticize this. This is what would be the solution to our game. Okay. So that's it for the solution of this game, in fact. And hopefully you've enjoyed our short lecture for today. Okay, we'll continue next week with the second part of these slides. Thank you very much and goodbye.